Hello everyone! Do you want to mock your software's dependencies so you can unit test it easily? Is refactoring with a dependency injection pattern not a convenient solution or not an option at all? Then keep watching and I will show you a technique that, while it should normally be your last resort, it does allow you to mock most dependencies without DI and typically without changes to your code under test. Before we move on, I will briefly introduce the concept of mocks and why it is useful when unit testing. Mocking dependencies is a way to limit the scope of a test or sometimes make it runnable on your host machine without requiring the availability of a large system stack. For example, mocks come in handy when you do not want to use a real database, for example, in your tests, or be forced to run them only on some specific hardware. Let's take a look at the following example to illustrate the usefulness of mocks. How can the function control speed be tested? It takes no input and returns nothing. It does have a side effect: it should control a motor. However, it seems unlikely we will be able to verify this on our personal computers in a scalable, quick, and convenient manner. The idea behind mocking is that instead of the actual dependency, for example a motor, the code under test will invoke another object, a mock, that we can control and set expectations on. Sounds straightforward. In other languages such as Java, it's easier, and in an ideal world where all code would follow the solid principles, it would be. Unfortunately, reality implies challenges. We have software never written to be testable, frameworks deeply integrated into the business logic, and many other factors that have resulted in code being tightly coupled to its dependencies. Code tightly coupled to its dependencies does not inherently offer the flexibility to invoke alternative dependency implementations. The implementation it depends on is very specific. That may not be an issue from a strict business perspective. For example, if we never plan to change those dependencies, no need to design for alternative ones. However, it does usually impede testing. This is because making the code invoke a different implementation, let's say a mock one, is not something the design has accommodated for. Normally, you would want to refactor so to break the coupling. As a rule of thumb, code that is loosely coupled to its dependencies is considered more sustainable and easier to evolve. One of the most popular design patterns that facilitates decoupling is dependency injection or DI. The idea is that instead of your code getting hold of its dependencies are provided to it, preferably via constructor arguments. This practice is part of the inversion of control principle, which promotes modular and extensible software. As you may have guessed, if we can inject dependencies, when testing we can provide a mock dependency instead of the real one. If you're not already following this DI pattern, I typically suggest to adopt DI. If this, for whatever reason, is not possible, then you can go for the technique I call static mock injection. However, I have to warn you, it does come with a cost. Before we delve into it, let's take a look at what you should normally go for if refactoring and DI are on the table. A quick disclaimer before we show code. Please treat everything you see as pseudocode. I will assume C++20 and I will not follow any particular coding guidelines or standards. I also have made no effort to optimize things. Your default choice when doing a dependency injection should be to understand what a dependency does and create an abstract interface out of it. Keep in mind that the interface should not only be abstract in name, but also in practice. In other words, if you were to substitute your current dependency with a different one that offers the same functionality, your abstract interface should be able to accommodate both implementations. After our refactoring, the car implementation does not depend on any concrete motor. As long as we provide an object that specializes the motor interface, the car class is happy with it. This allows us to pass the real implementation when building our software for production and the mock implementation when we want to run our tests. To test this using the Google Test Framework, we would inject the mock and set our expectations on it before invoking the unit under test. Setting expectations on a mock object means we specify the arguments as well as the times we expect it to be called. Additionally, we may define any actions you would like to perform upon a mock method call, for example, return a particular value or modify one of the input-output arguments. Occasionally, you may want to avoid virtual functions and inheritance. DI is still possible by having the type of the dependency defined during compile time using templates. There is still a relatively tight coupling between your code and the implementation. However, since the type of the dependency can be selected externally by the user of, let's say, the class or the method, we can inject a mock object in our tests. Dependency injection is straightforward when it comes to decoupling code from dependencies and facilitates the use of mocks in tests. However, what happens when you cannot use DI? Now, this is typically not the case, but may occur if you cannot change the current API. For example, you may be dealing with a legacy component or code that is part of a larger framework that imposes certain design choices incompatible with DI. Alternatively, it may not be desirable to expose any dependencies outside of the class that uses them. Furthermore, some may consider injecting dependencies more complex rather than simply instantiating them within the context that requires them. Finally, there may be some concerns regarding the performance of virtual function calls. There's a bad and ugly side to the dependency injection alternative that will be demonstrated next, so please do think twice before steering away from DI. Let's go back to the original example. The code we previously saw is now split into a header and an implementation file. This is done mainly for clarity when it comes to the CMake configuration we're going to show. It does not actually make any difference. To have the implementation we want to test use a mock dependency, we have to decouple it from the real one. We will not change any code. Instead, we will do this on the configuration level. When we build for production, we will link to the working dependency, otherwise to the mock implementation. The cleanest way to achieve this is by having the configuration targets of the code we want to test depend only on APIs. In other words, on function or class declarations. You should depend on dependency definitions only on the integration scope. For example, targets that build a binary or combine multiple libraries. In the CMake configuration, the target DC Motor API contains only the declaration of the dependency, just the header file. The target that contains the actual implementation as well is DC Motor, and we should depend on this only for targets that we do not want to unit test. car.cpp contains the code we want to test. Therefore, the related target, car, should only depend on the API target, the DC motor API. At the integration scope, we should depend on both the code under test and a target containing an implementation, otherwise we will get link errors. Our production target would depend on car and DC motor, while our test target would depend on car and mock DC motor. Let's take a quick look at the mock implementation. Mock DC motor is an almost classic Gmock implementation. It has two unusual characteristics. First, it does not inherit or technically have anything to do with the DC motor dependency. There is no inheritance, it is a class on its own. Second, it is implemented as a singleton. We will utilize the singleton pattern to ensure that both the business logic as well as the tests use the same mock without injecting anything. This is where the magic happens, the mock implementation of the DC motor dependency, which we link against when we build our tests. Please note, the mock DC motor class you saw before is not the mock implementation. The infamous mock implementation resides in mock-dcmotor.cpp and uses the mock DC motor class. It defines the declarations from dcmotor.h and merely uses the singleton class mock-dcmotor from the mock-dcmotor header file. Let's make this clear. The production equivalent of mock-dcmotor.cpp is dcmotor.cpp. In other words, the actual implementation of the DC motor class. If it makes it easier for you to see the equivalence, we could have had two dcmotor.cpp files, one in the production source directory and another in the test directory. In our tests, when the car class invokes a DC motor instance, the implementation that gets called is the one in mock-dcmotor.cpp. And since the singleton of the mock-dcmotor class is being invoked, we can set expectations on it without having to inject it. Our unit test starts by getting hold of the mock. Remember, mock DC motor is the very same mock that is being used by the mock implementation of DC motor that we previously saw. Then we set expectations on it as normal and we invoke the code under test. Despite no DI, we were able to mock the dependency and test the seemingly untestable control speed method. Aside of the boilerplate code to create the mock implementation and some changes in the configuration, it was pretty convenient to use this technique to statically inject the mocks into the code under test. Will this always be the case though? Let's take a look at some more complex cases. Here we have another car, cool car, which owns multiple dependencies required for its implementation. Note that there are two odometer instances and that there is no particular meaning behind the implementation. It is for illustration purposes, yet I hope you find it adequately realistic. Then we have the corresponding CMake configuration. There is nothing really new to see here. We follow the same technique as before. Code that should be tested, namely coolcar.cpp, depends only on declarations. In other words, only on APIs. The definitions are linked in the integration scope, for example, when it comes to production, the cool car main target. The same goes for our tests. Nothing new to see here. We provide mock implementations which relay the calls to the respective mock singletons. For convenience, since we will have multiple test cases, we create a test fixture called cool car test that gets hold of all the mocks and a cool car instance. There are no surprises when it comes to simple test cases. Verifying the functionality of turn works as expected. Static mock injections work well when the mocking scenario is simple. But what happens when things are more complex, or when a simple scenario like this one gets combined with more intricate ones? It has been implied a lot so far, but in case it wasn't clear, there are undesirable aspects of this technique. Let's take a look at some bad ones first. Since the mock definitions share the header file with the production equivalent, there may be implementation leftovers that need to be accommodated. Here we have a private member variable that is never used in the mock implementation, and some compilers or static analysis tools can emit a warning. This is not so terrible, but there could be more dependencies as private members that would have to be stubbed out. This means that there is a risk you will need a lot of boilerplate code to get your mocks working. Did you think we were going to use singletons and get away without any drawbacks? Sadly, they exist. As previously explained, each dependency instance calls the very same mock. We do take advantage of this behavior to set the expectations on the same mock as the one used by our code under test without having to inject it. There is only one mock instance we can set expectations on, regardless of how many times a mock dependency gets instantiated. To put this simply, despite having two instances of odometer in cool car, our tests have only one mock odometer. As a result, we set expectations on a single object, while in the actual code there are two. Cool car has the left odometer and the right odometer instances, while our tests only has odometer underscore. This inconsistency increases the complexity and decreases the readability of our tests, especially when our code handles multiple instances of each dependency. Unfortunately, this is not the only negative consequence of using a singleton. This was just the bad side of it. There is an ugly one too. All these test cases look fine and they worked. Well, to be exact, they worked individually. When combined, they may still work, but depending on the order, they can fail with a very unexpected error. Once we run all the test cases together, suddenly one of them starts failing. The error is very strange too. Gmock complains it was expecting to get the send method of logger to be called once with the argument turning right. Instead, it is called with the argument driving. But wait a minute, turning right is the argument of send in the turn method, not the drive method we are testing in the failing test case. We do not even set any expectations on logger when we test drive, so why did this show up now? Well, since there is one instance of mock logger, expectations are sticky and leaked between test cases. There is just one mock instance, the same instance for all the test cases. That's what a singleton does for you. From the mock's perspective, we have expected it to be called twice. Once with the turning left argument and once with the turning right argument. Instead, we called it 3 times. In case you did not already notice, there is a rather uninteresting call to send with the argument driving that we would typically omit from our unit tests due to its lower importance. Thankfully, there are 2 workarounds for this. The first one involves resetting the mock after each test case. This way, expectations set in one test case will not be leaked to the following ones. The second is about being very explicit and specifying expectations for all the calls to the mock. Needless to say, this can clutter your test cases and further decrease their readability. Personally, I go for the first, since I like my test case to be very focused and narrow. However, there is nothing stopping you from forgetting to add the necessary statements in teardown. And when that happens, as you show, you get some very surprising errors. I have become accustomed to them and can quickly tell the culprit. However, developers not familiar with the technique may be extremely baffled over the test failures. Overall, with static mock injections, the order of the test cases start to matter, which is generally regarded as a very bad practice. Moreover, you may need to explicitly set uninteresting expectations on mocks, which hurts the readability and increases the scope of your test cases. You can get unrelated tests failing, which may even be in the test cases belonging to different CPP files if they are all compiled into the same test binary. As explained, there are workarounds. However, walking on thin ice is usually not a situation you want to be in. There is a variant of the static mock injection that circumvents the undesirable side effects of the singletons. Now, the dependency type, motor, is determined during compile time as the class gets turned into a class template. DI is not needed, however, refactoring your code will be. In other words, this is not a drop-in replacement for the previous technique. Mock motor is a bit more complex now. The mocked methods are here again, however, we also maintain non-owning pointers to all instances. The order of creation determines the identifier of its instance in the map or the vector you have them stored in. If you know when a dependency was instantiated, you can get hold of it. Upon destruction, the respective non-owning pointer will be set to null. The biggest advantage of this static mock injection variant is avoiding leaky expectations. As long as you choose the right instance, you're good to go. However, ensuring this can be inconvenient or complicated the bigger your test suite grows. If you come to think of it, it does not completely eliminate dependencies between test cases. The order still matters as it determines the index of the mock you should fetch. Overall, my suggestion is for DI to be your default choice when decoupling your business logic from its dependencies and mocking them in your unit tests. Static mock injection can help you in some cases avoid refactoring, satisfy domain constraints, hide dependencies inside your class, and keep your constructors simple. This technique will not work if your dependencies are both declared and defined in a header file, since we will not be able to choose a different implementation during linking. In other words, you will not be able to mock any dependency. The title was slightly misleading. Static mock injection may make your life easier in the short run, however, it will not scale very well. It is good to know about, but should be used with caution and after having ruled out the alternatives.